ladies and gentlemen. I welcome you all to this lecture. Today we want to look at yet another important unit, and that is called vector spaces. So to look at vector spaces, we shall first of all understand what a vector space is. So let us look at the definition. So to talk about the definition, let us consider a non-empty set. If we consider a non-empty set V, where two operations that has got two operations, that is addition and scalar multiplication. Now, if this non-empty set here has got two operations, that is addition and scalar multiplication, such that every element that we pick from V, so we are picking U and V from this given set. If we are able to find a unique element, U plus V, that is also still in that given set, and also if we have U, which is an element of this given set, and we have a scalar A, which is obtained from a given field F, if we are also able to obtain AU also in this given set, then we shall be able to say that V is a vector space over this given field F if it will be able to satisfy some more given conditions. In other words, we are saying if you have a non-empty set which you want to check whether it is a vector space, this empty set 1, when you pick any two elements from this set, U and V, then U plus V must also be in that given set. You have picked U and V from that set, then U plus V must be picked from that given set, and we call this one here closure under addition. Then, if at all you are able to pick any scalar, so it can be any element from a set of real numbers. If we pick A from a given field, which we are denoting by F, such that when we also pick U from this given set, then we are able so to obtain A times U also in the same set. So we shall be able to define two things here. This is closure and addition, and this one here is what we call closure of the scalar multiplication. So this is closure under scalar multiplication, and this is closure under addition. So we should be able to obtain two things at first. That is, we should be able to show that closure under addition is satisfied and closure under scalar multiplication is satisfied. However, having shown that closure under addition and closure under scalar multiplication are satisfied, then we must as well satisfy about more 8 conditions. That is, if you pick U, V, and W from this given set V, and you pick A and B from this given field F, then you must also show that U plus V is same as V plus U. That is commutativity under addition. You must as well show that when you get U plus V again plus W, it is same as having U plus V plus W. And this is what we call associativity under addition. You should as well show that there is a vector in V which we denote by a 0, such that when you get U plus that 0 vector, you should be able to get U. In other words, you should be able to show the presence of an additive identity, in that the set that you are considering, you should be able to be having or to show that there exists this element or this a zero vector, such that when you get u plus that given element, you will be able to get u. And this should as well be same as having 0 plus u. In other words, when you get 0 plus u, it should be able to give you u, which should be the same as having u plus 0. So you should be able to show the presence of an additive identity. Number 5, that is 4. For every element that you pick from this given set V, for the element that you pick, that is, for example, u picked from V, you should be able to show that there exists a negative of this u, such that when you get u plus negative of u, you are able to get a 0. In other words, you should be able to show that for every vector that you pick from this given set, when you add there its inverse, you are obtaining 0, but this 0 is what we call the additive identity. In other words, this property number 4 says that for every element that you pick from V, you should be able to show that there exists another element in V in which you will be calling the additive inverse, such that when you get an element plus the additive inverse, you are able to get what we call the additive identity. So that is what this property means, that you get for any element you pick from V, there should be an element in V which is called the additive inverse, such that when you get u plus its additive inverse, you are able to get an additive identity. So that's why we say u plus negative of u, which negative of u is, because our additive identity is 0. So if I need to get the additive identity as 0 and I have u as my vector, then it means I must add there negative of this vector, such that when I add the 2, I'm able to get a 0. So that is, when you look at these, that is axiom 1, 2, 3, and 4, they are axioms associated to addition. These are axioms associated to addition. Then we talk about some other axioms associated with what we call a scalar multiplication. So to talk about axioms associated with scalar multiplication, we shall, first of all, we have already defined the closure under scalar multiplication. So the next one, for each element, if you pick 2 elements, that is u and v. If you pick 2 elements u and v from this given set, and you pick any scalar, which scalar we are taking, for example, k. If we pick any scalar k from the given field, then you must show that when you get k into u plus v, you should be able to get ku plus kv. You should be able to show this. So for any given scalar picked from F, then you have u and v, which are vectors from V. You should be able to show that when you get k into u plus v, it will be same as getting ku plus kv. And we call that one the distribution property. Then we shall talk about another property, which is still distribution property. And we shall be saying, if you have any 2 scalars, for example, A and B, which are scalars, the scalars are picked from the field, which we are calling F. Then for any 2 scalars, A and B picked from the field F, and you have any vector u picked from a set V, then you should be able to show that when you get A plus B into this u, you should be able to show that this is same as A times u plus B times u. So when you show this, this would be the property number 7. Then property number 8, still you are dealing with 2 scalars. So if you have 2 scalars A and B, we said a scalar. Scalars are picked from the scalar field, which we are denoting by F. and vectors are picked from this non-empty set which we are denoting by V. So if you have A into B times U, it should be same as having AB into U. So this one should be able to hold. That when you get A into B of U, you should be able to show that this one is same as AB into U. That is another property. And lastly, you should be able to show that if you have one picked from a field F, if you pick one from the field F, then you and U from the vector from the non-empty set, should be able to show that 1 times U is same as U, which is supposed to also be same as U times 1. So when you are able to prove these properties here, these are 8 properties, but which 8 properties plus the 2 properties of U plus V in V and AU in V. This is the property for closure and addition. This is the property for closure and scalar multiplication. So when you add them onto the 8 properties, you are able to achieve 10 axioms. So these 10 axioms are the ones that must be satisfied for a given non-empty set to qualify to be called a vector space. So we shall be saying that for any given non-empty set to qualify to be a vector space, then 10 axioms must be satisfied. If one of them fails, then that given set will not be called a vector space. In summary, we shall be able to say that a non-empty set V is a vector space if all these 10 axioms are satisfied. As we have said, we have axioms related to addition and we have axioms related to scalar multiplication. So basically, to talk about a given vector space, you must first of all define 2 operations on a given set. That is an operation of addition and scalar multiplication. And most importantly, that's why in our definition we are saying if V is a non-empty set that has got 2 operations, that is of addition and scalar multiplication. So these are the major important operations that must be defined on the given set, that is addition and scalar multiplication, because we have seen that other related axioms are actually based on the addition that you will have defined on that given set, and the scalar multiplication that you will have defined on that given set will determine on how to prove for commutativity, associativity, additive identity, and additive inverse. And the way you define your scalar multiplication on that given set will determine on how you will prove for these axioms related to scalar multiplication. So to define a vector space, you must have 2 operations defined on that given set, addition and scalar multiplication. So these axioms are these. There are 5 in each, making a total of 10. So we have 10 axioms that must be satisfied by this given non-empty set if it has to qualify to be called a vector space. So under addition, we have seen closure. Under addition, very important. So after defining the closure and addition, you will be able to define this because you will need to know how to add any 2 vectors in that given space. So again, to talk about axioms of scalar multiplication, we have already defined them. This is what we call closure under scalar multiplication, and the closure under scalar multiplication will determine on what to do and on how to prove the remaining axioms. So to prove these axioms, you need to know how to add any two vectors in that given set. To prove these axioms, you need to know how a scalar is operated on a given vector in that given set. So that is the summary or the definition of what we call a vector space. And a vector space must be defined, as we can see. To define a vector space, we must have a field. So this is a field, which field is where you will be getting your scalars. So the scalars can be real numbers. So when we are talking about scalars, we are talking about real numbers. Numbers like 1, 2, 3, such numbers I have. So any real number can call that one to be a scalar. So we shall be representing our field with capital F and a vector with a capital V. So if we say capital V, then we are talking about the vector, and elements can be represented by the small letters. So these are elements of the vector space. Let us talk about this one here. We have a note which says that elements of a vector space are called vectors or points, and we shall be calling elements of the field F as scalars. So when we are talking about vectors, we are meaning elements of the vector space, or we can call them points. Then we shall be saying that the scalar multiplication in a vector space basically depends on F. As we have seen, to define a vector space, you must first of all define two operations, that is for addition and scalar multiplication. And there is no way you can define the operation for scalar multiplication without having scalars. So you must have scalars to define scalar multiplication. Now, scalars are obtained from the field. So we shall be saying that scalar multiplication in a vector space typically depends on F, because F is our field, and that is where we obtain scalars. Thus, we shall need to be precise and say that V is a vector space over F, instead of simply saying V is a vector space. So whenever we are defining a vector space, we shall be defining a vector space together with a field. So you will be saying that this is a vector space over this given field, meaning that we cannot have a vector space without defining the field. So we shall be defining a vector space together with its field. So we shall be saying V is a vector space over a given field F, instead of simply saying V is a vector space. To talk about some few examples of vector spaces, for example, you can say R at power n. R is a set of real numbers. So when you say R at power n is a vector space over R, it means that R is our vector space. That is R at power n is our vector space. Then this R is our field. So it means our scalars will be real numbers. Then when we say C to power n is a vector space over C, it means C will be representing our vector space, but C to power n will be representing vector space, but C will be representing the field. So you are saying C to power n is a vector space over C. It means C to power n is where we are obtaining our vectors, and scalars are obtained from C. We shall be looking at examples on how we can easily show that a given non-empty set is a vector space, whereby we shall also be able to define the field as well. Let us talk about vectors in R to power n. Clearly, we have seen that R at power n is a vector space, over R. Is a vector space over R. This is our field. This is where our scalars will be obtained from. So we need to know what are vectors in Rn, or how are they? Because if we are to talk about the axioms that we have looked at, we must first of all know the vectors in Rn. So to talk about vectors in Rn, it is important that we first talk about an ordered n tuple. So we shall be saying an ordered n tuple simply represents a vector in any space. For instance, we have always talked about such vectors. You have vectors arranged like 1, 2, and 3. You have vectors like 2 and 3. You have vectors like 1, 2, 3, and 4. So if you have this as your vector, for example, you have this as your vector, this as your vector. So we have got some simple names for such vectors here. For example, if there are 3 of them arranged in form of x, y, and z, if they are arranged in this form, then we shall be saying this is an ordered triple. This is an ordered triple. Then when we look at such which are in form of xy, we have always been dealing with such numbers here in form of xy. So such numbers here are, we have always seen such numbers here, and for these ones here we call them an ordered pair. So this is an ordered pair. Then when we have 4 of them, then we call them an ordered quadruple. An ordered quadruple. So if you have an ordered pair, you have an ordered triple, you have an ordered quadruple. So the trend continues. It might not necessarily be up to 4. It can be up to 5, 6, 7, and so on. So when we have such vectors arranged in form of x1, x2, x3, up to xn, if we have such numbers arranged in this form here, then we shall say that these ones here form an n tuple. Like the way we say this is a triple, this is an ordered pair, this is a quadruple. So when we talk about any of them, so we say it is an n tuple. So when we talk about vectors in R to power n, then we look at the set of all n tuples in any space, and this will be simply represented by R to power n. So R to power n will represent the set of all n tuples in any space. So it means that elements in R to power n, are the elements of the form x1, x2 up to xn. So when you have such elements, we say these are the elements in R to power n. If they become 2 of them, you have x1 and x2, then you say these are elements in R to power 2, like that. So we shall give some simple names. Especially we have seen that R to power n, if it is R to power n, that is an n tuple. But now, if it is R to power 1, that is when n is 1. When n is 1, then we call this as a set of real numbers. When n is 2, we call 2 space. This is a 2 space. If it is R to power n, this is an n space. So if it is R1, that is 1 space, because our n is 1. And that is called the set of real numbers. When n is 2, then we call this one a 2 space, and a 2 space, and that is a set of all ordered pairs of real numbers. 3 space, that is when n is 3, then we call this one a 3 space, and of course this would be a set of all ordered triples of real numbers. And the trend continues up to Rn, which is an n space, and we call this as a set of all ordered n tuples of real numbers. So an n tuple, which is, when we talk about n tuple, we are talking about x1, x2 running up to xn. So this one here can be viewed as a point or as simply a vector. When you say x is equal to that, so it means our x is an element from Rn. And if x is an element from Rn, then x is same as x1, x2 up to xn. So x is having such element because x is an element of R to power n. So if x is an element of R to power n, then x must have elements from x1 up to xn. So we can simply view this as a vector or as a point. where these xi's are simply the components of this x. These are the ones that make up the x, because you are saying x is an element in R to the power n, which means x has components x1, x2, up to xn. Then, when we talk about equality of elements in R to the power n, to say that, for example, x is an element in R to the power n, and for that case, x is this. You also say y is an element in R to the power n, which means y can also be in the form of y1, y2, up to yn. So if you are able to say that x is equal to y, x to be equal to y, it means that x1 must be equal to x to y1, because you are saying x1 up to xn is equal to y1, y2 up to yn. For these to be equal, then x1 must be equal to y1. In other words, these corresponding elements must be equal. x1 must be equal to y1, x2 must be equal to y2, up to xn must be equal to yn. Meaning that the components of R to the power n are only equal if the corresponding components of these two vectors are equal. That is, the xi must be equal to yi for all the values of I. This must hold for you to say that x and y are equal, if x is taking this and y is taking that. So, we have clearly seen that for two n tuples to be equal, then xi must be equal to yi for all the values of I. In other words, we shall be able to say that this, that is, this n tuple is equal to this only when x1 is equal to y1, x2 is equal to y2, x3 is equal to y3, and so on up to xn is equal to yn. Then R to the power n is a vector space over R with operations of coordinate-wise addition and scalar multiplication defined as, if we have u and v picked from R to the power n, if we have two vectors u and v picked from R to the power n, then it means u will be in the form of u1, u2 up to un. V will be in the form of v1, v2 up to vn. So, for addition of any two vectors from R to the power n, that is u plus v, then we shall add component-wise. In other words, you are having u1, u2 up to un. So you are adding there v1, v2 up to vn. So when you are adding these elements here, you add component-wise. So u1 will be added with v1, u1 will be added with v1, u2 will be added with v2, and the same continues up to un will be added with vn. So this is how we add any two vectors picked from R to the power n. Then when we talk about scalar multiplication, if we pick u from R to the power n, then we have also c from R. If we pick u from R to the power n and c from R, our R is our field, c is a scalar. So for that case, we shall obtain c of u by multiplying c into the elements of c. So this will be c into u1, u2 up to un, which is same as cu1, cu2 up to cun. So this is what we obtain when we multiply a scalar into the vector which is picked from R to the power n. Then let us take a note of this. When we talk about a zero, if we talk about a zero picked from R to the power n, then it means this zero will also be in the form of 0, 0 up to the last term, which is the nth term. So when we talk about 0 picked from Rn, that is the 0 vector from R to the power n, then it will be of this form. Likewise, the same way we have done for u. If u is an element from R to the power n, then it has n entries, and that same applies to 0. When we talk about a 0 vector from r to the power n, then we are simply talking about a vector that has got n entries that are all zeros. So to say that r to the power n, r to the power n is a vector space over the field R, then we shall be able to prove or to show that r to the power n satisfies all these 10 conditions. Remember, we said that for a space or a given non-empty set to be a vector space over a given field, it must satisfy 10 axioms. So, and this r to the power n is a vector space over R if it satisfies all these axioms. But we shall be able to see how best we can prove all these axioms to show that r to the power n is a vector space over R. But r to the power n, as we come to examples of vector spaces, r to the power n is a vector space over R, meaning that it satisfies all these 10 axioms. So we know how to deal with addition of any vectors from r to the power n. We know how to deal with scalar multiplication of any vectors in r to the power n, which means we can easily prove each of these axioms here. But we shall look at examples on how we can easily show that r to the power n is a vector space over R. But at the moment, you should even be able to prove all this because we know how to deal with addition of any two vectors in r to the power n using component-wise addition. We know how to deal with the scalar multiplication, because if you know how to add any two vectors, from there you can easily show all these axioms that fall under addition. If you know how to deal with scalar multiplication of a vector and a scalar in r to the power n, then you can as well easily prove these axioms related to scalar multiplication. But we shall look at an example on how best we can easily prove that r to the power n is a vector space over R. Let us look at some few examples of vector spaces. So we talk about example number 1, which is the space k to power n. When you try to relate this with r to power n, actually they are related spaces because this is r to power n and this is the space k to power n. So they are almost the same. So meaning that whatever we talked about for r to power n applies for this space which is k to power n. So let us talk about this space k to power n, and basically we shall be looking at two things, that is vector addition. How do we add vectors in this given set, and how do we deal with scalar multiplication? Remember, these are two major things that we need to know, especially if we are to prove that a given set is a vector space. You need to know how to add any two vectors in that given set. You need to know how to deal with scalar multiplication. When you know the two, then you can easily prove all other related axioms for addition and scalar multiplication. So we shall say that if k is any arbitrary field, then the notation k to power n is frequently used simply to denote the set of all n tuples of elements of k. So like the way we said for r to power n. So this set here, when you talk about k to power n, you are simply talking about all the n tuples, or the n tuples of elements of k. N tuples of elements of k. That is what we talked about. So we shall be able to say that k to power n is a vector space over the field k using these operations. When we talk about vector addition, as we have seen, if you pick any two vectors, u and v, from this given space k to power n, then what will be u plus v? That is the vector addition. That is how we shall be adding any two vectors from this given space. So we shall be able to say if u is picked from k to power n and v is picked from k to power n, then it means u has got n elements. So for this case, we are using elements a1, a2 up to an. So we shall be adding the elements of v, which we are taking to be b1, b2 up to bn. So how do we add? Like the way we added the elements in r to power n, we use component-wise addition. A1 with B1, A2 with B2, up to AN with BN. So this is how we add elements in vectors in the space K to power n, more related to R to power n. Then when we talk about scalar multiplication, we are multiplying K with any vector. For example, if K is picked from the field K, if this K is picked from this field K, and we have u picked from k to power n, then you can easily get ku by simply multiplying k into each elements of u, which is a1, a2 up to an. So we simply multiply k with each of the elements of a1 up to an, and this is what we obtain. So likewise, we can easily define the zero vector in k to power n, and this zero vector will be simply the n tuples of all zeros. In other words, when we pick 0 from k to power n, then this 0 will be same as the elements for all the elements of zero of this given vector will all be zeros. So that is the n tuple of zeros, like the way we talked about the zero vector in r to power n. So it will be almost the same. Then let us talk about if you are interested in the negative vector of any vector in k to power n. So if we have u picked from k to power n, then what will be negative of u? Negative of u is simply negative of a1, a2 up to an, and this negative affects all of these entries here. So that's why we shall have negative a1, negative a2 up to negative an. Let us talk about another space, which is a vector space. That is what we call the polynomial space P of t. So P of t is a set of all polynomials that have got the form of this. So it means P of t is an element of P of t. So if P of t is an element of this set here, then we can represent P of t as a naught plus a1 of t plus up to as of t of s. But s is taking up elements from 1, 2, and so on. Now, this given set here, we are majorly interested in how do we add the vectors and how do we deal with the scalar multiplication of vectors within this given set. Now, looking at this, given a polynomial P of t that has got a1, a0, a1, a2 up to as. These are what we call the coefficients, and these are degrees. Degree 1, degree 2, up to the degree s. So P of t is a vector space over a field F when we use the following operations. That is, if, for example, you pick P of t and Q of t from this given set, which is P of t. This is capital P, and these are small. That is P and Q. Now, we need to deal with addition. That is, you are getting P of t plus Q of t. So how do we add any polynomials from this given set? We use the usual operation of addition of polynomials. So in case you are dealing with a polynomial P of t, let me take some small example. P of t is 1 plus t squared plus t, then plus 2t squared. Let us take that one to be our polynomial P of t, and Q of t to be, for example, 2 plus 3t plus maybe 3t squared. So these are polynomials of degree 2. So it means that your s is 2. Now, looking at this, we are saying, how do we add? How do we get P of t plus Q of t? We add the two by simply adding the corresponding terms. So 1 corresponds to these are constants. with the coefficient of t as t to power 0. So these are coefficients of t, which t is to power t of power 0. So when we are adding, we get 1 plus 2, which will give us a 3. When we are adding, we add this one with this. So you don't add the t with 3t squared. This corresponds to this. So when you are adding, you get t plus 3t, which is 4t. You get 2t squared plus 3t squared, which is 5t squared. So you add using the usual operation of addition of polynomials. So when we are adding polynomials, remember we add constants alone. We add the corresponding terms, that is for t. So this is what we get, and that is how we deal with the addition of polynomials. Then to deal with the scalar, when we are talking about scalar, for example, you are having a 2, you want to multiply p 2 into p of t, so it will be 2 into 1 plus t plus 2t squared. So which is same as multiplying 2 on each of these, that is 2 plus 2t plus 4t squared. So when we talk about scalar multiplication, if we talk about k, k is representing all scalars. Then times p of t is our polynomial that we have picked from this given set. Then this one here, we use the usual operation of product of the scalar k and the polynomial of t. But this is majorly what we are talking about. If you are multiplying a scalar 2 into p of t, then you multiply 2 on each of these elements here. Then we shall finally say the 0 polynomial 0 is actually the 0 polynomial in p of t. So this 0 will simply denote the 0 polynomial. Of course, when you talk about the 0 polynomial, you are talking about 0 of t to power 0 plus 0 of t to power 1 plus 0 of t to power 2, like that. So this is our 0 what? Our 0 polynomial. So this is 0 equaling to all this. So this will be the 0 polynomial in that given set. So we shall be able to look at some more examples of the vector spaces in our next lecture again.
Yeah.